We're in Chapter 9. We are talking about synchronous machines. And after what was one lecture of a lot of electromagnetics and material that was sort of like a precursor and background, we got to the payoff, which was actually looking at how synchronous machines work using this assumption or simplified system of connecting it to an infinite bus. And we could examine how the output, the real power output, was affected by delta, which in this case is represented or represents the difference between the phase of the infinite bus and the phase, the internal phase of EAF, which again represents the induced EMF on the coils due to the flux linkage between the field winding and the stator windings. And we were also able to see how that affected stability. And for this idealized case, we have stable operation up until delta equals 90 degrees. After that point, we reach an instability. And that makes sense when we take a look at how this graph, if we take a look at the slope, right, in essence, when we reach the instability, we're trying to increase the P gen hour P load, depending on which end of the graph you're on. We're trying to increase the P gen output, which is causing delta to increase, but we can no longer do that, so it begins to come down. So we used the analogy last time of pushing the gas pedal on a car, but beyond a certain point it actually causes the car to slow down, right? That would cause, well, not necessarily instability, but it would definitely be an unpredictable way for the car to work. In this case, it causes the instability. So now we're going to move on to finishing Chapter 9. Let me see where we are in these notes here. Okay. So before I start a new sheet of notes, I'm going to add one or two things to this set of notes from last time. So what happens if we want more power from our generator when we are operating between, with a delta value between 0 and 90 degrees? So assuming no loss, which we are in this case, PM equals PE, the mechanical power equals the electrical power. To supply more electrical power, we let more steam into the turbine, which in turn increases the mechanical power supplied. The rotor will speed up for a short period of time, increasing the delta value before F returns to 60 Hertz. And we will reach our new steady state, which we can call PM2 or PM3. We'll number them accordingly, where delta 2 is larger than delta 1. Again, with the result being that because our rotor speeds up for a small period of time, the delta will increase. Now, if we real quickly, yes.
So just to clarify on that,
Yes. If you're at steady state, you should not be migrating. The delta should only be changing during the transient periods. Yes?
If you're at 90 degrees, would you ideally not want your delta to be at 90 degrees? Because it could potentially, go over or under.
Yes. So most definitely, you want to stay away from the edge of stability. Another issue, which we talked about a little bit last time, is that this is a very idealized case. No internal losses, the transmission line losses are zero. In reality, you would never get anywhere close to 90-degree separation between two adjacent buses and stay in stability. The value is much, much, much smaller, and you actually can't predict it without doing a much more substantive analysis. So number one, the range is smaller. Number two, you don't know exactly where the edge is. Okay, it's not like, in this case, you stay away from 90. The edge could be 8 degrees, 15 degrees, 20 degrees. And so you're estimating the edge and also trying to stay back from it significantly. So yeah, you definitely want to stay away from that. So the last thing I'm going to put here is, what's the bottom line? Okay. The bottom line is, well, there's a couple of them here. For delta greater than 90 degrees, we end up with what's called a negative feedback loop, right? So we increase the mechanical power supplied to the machine, more steam, more energy coming in, and the electrical power starts going down. So you can see how that would play havoc with our control system. And I'm going to add that note here. So this sequence is called voltage collapse or loss of synchronism. Loss of synchronism. And this is right the beginning of a blackout. And last thing, which I'll write down, we've already said it several times. Okay, in reality, the limits of stability are much smaller. Okay, so that's all I wanted to add to these notes to sort of complete this section 9.4. So now let me start a new set of notes here. And how much do we have left in chapter 9? Overexcitation. Okay, I think we should get done with chapter 9 today. So, we had been talking about the two different ways that we control a generator. One of them, which was the subject of section 9.4, was the mechanical power going into the generator, right? That controls PM predominantly. Does anybody remember what the other predominant, the other control input we have, or predominantly, there's a lot of control inputs, but what's the other main control input for the generator? It's heavily linked to Q, to reactive power. Say it again? Indirectly, the excitation, right? We said that the amount of current that we supply to the field winding, okay, will have a huge effect on Q. So we control P through the throttling of the steam into the generator, or whatever our mechanical input is, and then Q through the field winding. So section 9.5 deals with this other control variable. So we're going to talk about field excitation for reactive power control. Okay, so in the previous section we were playing around with PM. I don't know if we explicitly said it, but we were assuming that the excitation was constant. Here we're going to be doing the opposite. We're going to be playing around with IF. We're going to be assuming that the PM, the mechanical input, is constant. The reason for this, in not so many words, is that it's really difficult to look at both at once, and the relationship becomes highly nonlinear, and it's very difficult to learn anything from that. So if we want to be able to at least use this for teaching purposes, we gotta limit our manipulation to one of the two variables at a given time. And we know, we've talked about this before, we know we can control Q with IF. All right. So now I'm going to draw, I don't know why my iPad keeps doing this, where I got to draw this line and make it scroll down. It's weird. So we're going to draw a figure from the text and discuss it. So this is figure 913. And so we're using the same circuit model that we have for quite a while now. We have our EAF. We have our synchronous impedance. And we have our terminal voltage. So this is sort of the simplest, again going back to the previous section, the simplest representation we have of the generator. And so for this case, we can draw the vectors that represent its behavior. So, and we'll see what that means in 1 second. So what I'm going to do is, okay, so we start off at the origin, and all I'm going to do is just draw these EAF, IA, VA, etc. And so for figure 9.13, we're going to assume that we have a unity power factor. So let's start off by drawing the case for unity power factor. So we have our VA. So the one thing we know, if unity power factor applies, what's the angle of VA going to be? 0, right? Or actually, no, that wasn't a good question. VA is always going to be referenced to be, sorry to backtrack on you, and it was a good answer regardless. VA is normally going to be the reference for our system, so VA is going to be 0 regardless. The question I meant to ask was, what's going to be the angle of IA, which the answer is going to be 0. Okay, so I'm going to draw IA just a little bit below it. They're supposed to be right on top of each other, so you can imagine that they're right on top of each other, but I want to show them as being distinct. Okay, and then using the beginning to end or tip to end method, we can determine what EAF would be. So EAF is equal to the voltage drop across the synchronous reactance plus VA. So let's add in what the voltage drop across the synchronous reactance would be, which is going to be JXS times IA. JXS has an angle of 90 degrees. IA has an angle of 0 degrees, which means that this is going to point straight up, like that, right? And then our EAF is going to be the sum of those two together. So our EAF is going to look like this. So the red, yeah.
Can you explain once more why that's vertical?
Yeah, because if you take a look at the angle of this, you have XS with an angle of 90 degrees, okay, which is the same as J times XS. And then you have IA with an angle of 0 degrees. So that just gives you 90. Okay, so this right.
That's a polar coordinate, or not polar, but complex coordinate system.
So this is a complex coordinate system. You can represent it in either rectangular or polar. Yeah.
I just got the terms.
Yeah. So depending on whether you describe it as real and imaginary or the magnitude and the angle. Yes.
If we're only caring about voltage, why are we graphing IA?
Well, because we need IA for this.
Oh, okay.
Right, we need IA to determine what the voltage drop across the synchronous reactance is. Okay, so this right here, the red depicts unity power factor. Now, to add to this, if our arrow were to point off in this direction, okay, to lean to the right, this is going to be the case of overexcitation. And if we have the case of it leaning to the left, okay, this is going to be under excitation. And what does that mean? Is here Q is going to be greater than 0. Over here, Q is going to be less than 0. So the terms overexcitation and underexcitation are, they reference the amount of DC current that's applied to the field winding, but they also directly reference the Q value.
Just
Yes?
to reiterate, the lines that you're drawing, the overexcitation and underexcitation, that would have been if you had some other JXSIA.
Well, actually, that would be if,
It had some real components to it too. So
well, if IA were not 0, right, or did not have an angle of 0, then that would cause it to tip to the right or to the left, right? If the angle of IA were 10 degrees, it would move to the right. Negative 10 degrees, it would move to the left. So it's actually, yeah, if we look at this right here, what causes this to change, that's going to be the angle of IA. Because JXS, that's not, I mean, that's not going to change. It's always going to be 90 degrees. Oh, I see what you're saying. So if there's a resistive element too, internally, that would also cause it to move. In most cases, we're not going to consider the RS value. It's going to be very small, because really what it represents is just the resistance on the windings of the armature, and that would never be large compared to the reactance value. So in these cases, it's going to always be the IA, the angle of IA, that causes that to move back and forth. So why did we draw these diagrams? In this section, so we're going to use diagrams like this a lot in order to study the effect of excitation, which you can see by the purple and the gray lines begin to show that a little bit. And right, but it's the vector diagrams are nothing more than just using this simplified version of the generator model and drawing the vectors that go along with it. And the real aspect that's going to change that we have to be worried about is this angle of IA, right? Most everything else is only going to change in terms of length. VA may get longer or shorter. JXS may be longer or shorter. EAF longer or shorter. Okay, so now, overexcitation. So overexcitation In a nutshell, too much IF, Q out is going to be greater than 0. And so how do we know that mathematically? So because the three-phase power is assumed to be constant, then we know that EAF sine of delta is also constant. Now, where is that coming from? That's coming from the notes last time. If I can find it. Right here. Well, is there a better version of that equation? I guess not. Right here. Okay, this equation 911 tells us that, right, the magnitude of EAF is going to stay the same. The sine of delta is going to stay the same. We already know that the infinite bus voltage is set, and XT is not going to change either. So if real power stays the same, EAF sine of delta will stay the same. That's that right there. Okay, so then, IF is the only thing that can change here. And actually, there's a better statement to put next. I'll write that statement again in a second. We know that EAF sine delta is constant, but that allows both So the product of the two must stay the same, but that doesn't necessarily mean that the individual values need to stay the same, right? EAF can go down while sine delta goes up. Sine delta can go down while EAF goes up, as long as our power, real power, stays the same. Okay. So I'm going to draw a figure that looks pretty similar to this one here. It's a little bit of repetition, but now we're going to draw it bigger. We're going to go into a little bit more detail. This was sort of like the preview version of it. And we're also now in this picture going to consider both generator and motor modes of operation. in this one, in this picture, this was strictly the generator mode of operation because the P out value is going to be greater than 0. Now we're going to consider both. There's a pretty good chance, as you can see, that the quiz next Monday is going to require you to draw some sort of figure like this. That's 50% chance at least that's going to be part of the answer. So, and that is a pretty significant part of the homework problems. If anyone has taken a look at them yet, a lot of the answers are the vector diagrams themselves. Okay, so drawing this one more time, starting at the origin, and what we're going to do is we're going to draw two different versions. I'll draw quickly since we've kind of already done this once. We have our VA. Okay, I'll draw the overexcitation case in blue and then the underexcitation case in green. So 1, 2, 4. So this is our J, X, S, I, A. And in this case, this is where our IA, right, will point downward. And what that corresponds to is the fact that we have a lagging power factor angle. Okay? Our IA lags behind our VA. And then for this case right here, our EAF, again just using the end-to-end method, will look like that. The other case is going to be in purple. So where we have now our IA would be leading. Running out of room a little bit, but IA is leading, which will then cause our JXS vector to point in the other direction, and now our EAF will do this. Okay, obviously this point right here would represent the unity power factor. Okay, so now on this we can determine both the P and the Q output. There's a little bit of repetition here, but right here we have P gen is greater than 0. Here we will have P gen is less than 0. So whether our EAF vector falls on the top half or the bottom half of this graph, that'll determine whether you have a generator or whether you have a motor. Okay, both of these cases are generators. So we'll call these the generator cases. And then down here, this would be the motor case, where it's absorbing power.
Does that really get with the current's negative, or the IA is negative? In terms of like, well rather,
Yes.
yeah.
Yes. So, and then we can draw a similar set of arrows here. So we have Q gen is greater than 0. We already labeled this before, but I'll label it again. Over excitation. And Q gen is less than 0, and we have under excitation. Sure.
Do we know whether or not Pgen is greater or less than 0?
Say it again.
The Pgen, where,
So essentially what you're looking at is this point. This is always the point that you're looking for. Where does this point fall? If it falls above the x-axis, it's gen. If it falls below the x-axis, it's motor. If it falls to the right of the second red dotted line, it's overexcitation, overexcited case. To the left, underexcited. So I should have made that clear. Yeah, it's this gray point right here. That is what we're looking at, which is essentially the endpoint of the EAF vector.
and when would it be less than 0?
If it's a motor case, if IA is less than 0, it would be absorbing power. Yeah, and we could try to draw a third case in there real quick, which I'll just draw as a dotted line. So if we had one that looked like this, right, then our V would, make sure I'm doing this quickly, so this would be negative. Right, it would look like that, and then you would have your EAF extending out.
And that's IA, what's the next row?
This would be the IA, and this would be the JXSIA.
Got it.
And then the EAF would extend out like that. I'm going to erase it just because I think it's making the diagram look really cluttered, but and when you do some of the homework problems, there'll be motor cases in there where you'll be responsible for looking at that.
Dr. Deese?
Mm-hmm.
What are we mentioned allowable cases for the previous subject. Like what are allowable like sources of error for this? Like 1 degree, or does the power factor angle have to be perfect for like the real world?
Oh yeah, I see what you're saying. Well, I mean, this is, yeah. I mean, it's the good thing about this is we're not really using a hard threshold, like a 90-degree threshold, where we could say, okay, that's not a realistic threshold. Really, now we're just looking at the relationships: overexcitation generator versus underexcitation motor. Those relationships will stay the same regardless of what assumptions we lose. Now, you can obviously see, right, that this vector right here, right, if we include the synchronous resistance, if we were to include a transmission line in between the infinite bus and the generator, then that would cause it to, the direction would be altered, okay? Where this difference here would not be equal to the same theta value. So that's part of, part of what would be affected. Erasing the whole thing here. And also, the biggest assumption we're making is the infinite bus, right? The infinite bus itself, that case is very, I mean, there's an assumption built in there. So, I mean, what we'll see, the next, not the next subject, but one of the later subjects we're going to talk about is load flow analysis, which is how do we actually analyze a power system with multiple components in it. And what we'll see is that this type of, work that we're doing here is great for understanding the way that a generator operates, but it doesn't really translate over to trying to solve an entire system. So, so that's the lesson. I mean, this chapter is focused on the generator, on the synchronous machine. So we're learning about it and assuming that the rest of the world, not that it doesn't exist, but we're using the infinite bus to act as an aggregate of the rest of, of the power system. So there's a lot of assumptions still that we're using in this right here. Okay, now, what is an interesting conclusion that we can make from this picture? So if you look here, that gray dot, right, that is moved right or left by extending the EAF vector, right? And the one thing that I haven't drawn on here is you'll note that both of the points fall on the same level, which we're going to call the constant real power I'm just going to call it real power level. In a previous textbook I used, they call it the real power locus. I don't know exactly how that term is applicable there. But so again, using the assumption that we have to, that the gray dot has to stay somewhere along that green line because we have said a priori real power output's not going to change, then you can see just by lengthening or shortening EAF, we're pulling it into underexcitation or pushing it into overexcitation. How do we lengthen and shorten EAF? By changing the IF value. And if we go all the way back into stuff we did from the previous lecture, you would see that that's the case. So that's how this very busy figure right here illustrates the relationship between IF and Q jet. And so that's really all there is to overexcitation, underexcitation, as far as we're going to be concerned in this class. If you can draw these figures, if you can do the calculations that are associated with them, which is just KVL, right? Then you should be able to handle all these problems. Underexcitation. Everything's the same, right? Just the opposite sign. And section 9.6 is something called automatic voltage regulation. Okay, and fortunately or unfortunately, depending on how you look at it, we're not going to go too much into this section because there were some other topics that I wanted to hit on, and I had to make some choices. But if you read the text, you'll see that it talks about how field excitation may be used to regulate the terminal voltage. But we are not going to be quizzed on that, and we're not going to be talking about that heavily in this course. Now, section 9.7, we are going to be diving into. So section 9.7 is synchronous, transient, and subtransient reactances. With some very bad spelling there. So we've already talked about what the synchronous reactance is, right? That's the value of excess that we had been using in our circuit model so far. And that is applicable for the case where we are at steady state, where the units are synchronized with one another. So, like I said, XS assumes steady state. However, there are other values that may be used shortly after disturbances. Hence, as the name suggests, right, during transient time. So synchronous reactance works during steady state. Transient and subtransient, which we'll talk about the difference between those two, are applicable during transients. Now, during the transients or the oscillations, the reason why we can use the word oscillation sort of as a synonym for transient here is because, right, for your generator, often the transient is going to be an oscillation, right? It's going to swing back and forth on either end of the steady state value, which is different than if you, like, when you talk about the transient for an RLC circuit, right? It wouldn't make any sense to use the term oscillation there because it just has this exponential return to whatever the new steady state value is. Okay, so during transient or oscillation times, the generator, well, it's a meaningless statement. During the transients, the statement says, during transient times, the generator is in a transient state, which is redundant. Okay, so now, to study transient phenomenon, our circuit model needs to be adapted a little bit. And so what you'll see is that there's two different ways that we can analyze the transients. One is to just use simulation, which is right, going to give us a more accurate result. So it'll be more accurate.
Will that be like spice or a different type of
Yeah, like spice. More accurate, more difficult, although one could argue that the difficulty level nowadays is low because computers are everywhere and it's relatively cheap, but still it's going to be more difficult than using the other option, which is the constant flux model. So this is going to be a less accurate but real-time analysis that we can do. Right, what that means is we can calculate the answer on the fly. And it's going to be easier, so it's going to be less difficult to do the analysis, hence the reason why it can be done in real time. And it's going to use some assumptions. Again, spelled that wrong, but so simulation or something called the constant flux model, which we haven't introduced yet. We're not going to go too much into simulation. I think that most of you are pretty comfortable using SPICE, and actually in the lab that you're doing right now, you're going to be required to set up a power system in SPICE. So you could take a look at some transient stuff potentially in that lab. It doesn't ask you to, but you could. So we're going to focus on the constant flux model, which again, a lot like this analysis up here, is more focused on teaching us how synchronous motors work, synchronous generators work, and is not so much the type of analysis that we could use for some sort of a large system study. Like you, more times than not, would not employ the constant flux model to determine the transient for a system with multiple buses. It just, your assumptions would pile up too much and you would end up very far from where you need to be. All right, so next section is 9.71, which is the constant flux model. Okay, so a generator is designed to supply constant IF in the steady state. This makes sense. In a steady state, we don't want any of the values to be changing, including Q. Okay, and so our IF would be held constant. Therefore, we may characterize IF as a resistance. In terms of a resistance, equivalent resistance value. So what we'll say is that IF is equal to whatever the voltage is applied across the terminals of the field winding divided by this RF value. So we can also assume that VF will be constant across the field winding terminals during a transient because the hardware lacks fast response capability. So whatever device you have connected to the terminals of the field winding, it can't react on the order of fractions of a second in order to try to account for whatever is happening during the transient periods. So it's slow, meaning that we can just assume that it's a constant value during the transient periods. And so what this does is this allows us to model the field winding as a short-circuited coil with a very small resistance. So, what is the big question here, going back to the title of this section? What is the constant flux linkage theorem? Okay, it states that the flux linkage of a short-circuited coil that has a very large time constant remains the same. And that's the linkage with the stator that we're worried about, right? So what is that really saying there? We have a transient, okay? Something happens to the generator, the rotor goes wild, okay, in terms of the speed variations. It starts speeding up, slowing down, speeding up, slowing down. There's two different things that could cause IF to change, okay? One of them would be if the mechanism that's supplying IF tries to respond. We've already said that's not going to happen because whatever that hardware is, it's really slow. So that is not going to be an effect. The other thing that could cause IF to change is the mutual flux between the stator and the rotor, right? They both have an effect on one another. So if the rotor is going crazy and the stator currents are all over the place, that could cause IF to change. The reason why it's not going to change is because the way that we're modeling the field winding during the transient has a very large time constant, right? Very large time constant means that changes are very slow, and right, it's like the exponential, the RLC circuit, right? The exponential response where that slope is very drawn out. It takes a long time for changes to happen. So both of those combined together, the slow reaction of the hardware that generates VF or IF, combined with the large time constant of that coil, means that IF is going to be staying the same. So therefore, under transient conditions, we can make the following statements. So, under transient conditions, the stator currents, armature also, same word, armature currents may change quickly. Right? We haven't said anything that limits the stator currents from going wild and being all over the place. We've been talking about the field winding. And to clarify some of the language that I was using previously, I think I may have been using IF where I should be specifically stating the flux linkage stays the same. So IF can change, but the flux linkage between the stator and the rotor, that must stay constant, which will translate, we'll see in a second, to our internal EAF being constricted. So, that's what the constant flux linkage theorem states. It's simply that the flux linkage between the rotor and the stator will stay the same during these fast-moving transient periods. So the next question is going to be, okay. So this may seem like a question that's out of nowhere. Okay, we're talking about these transient or subtransient periods. We've talked about this constant flux model. What is this question? What does that mean? How do the magnetic field lines connect the rotor and the stator? But what we'll see is that's an important question to ask, because the way those connections, I don't want to say are made, but the way those connections exist will be different depending on what transient period we're in, how fast things are moving, and that is ultimately what's going to lead us to the answer, which is alluded to as the title of section 9.7, synchronous transient and subtransient reactances. So what we're trying to do is define different values for XS. We're going to call it XS, XS prime, and XS double prime, which we're going to replace in our circuit model. Something looks like this, depending on whether we're talking about steady state, a transient, or a very fast moving transient period. Subtransient is, again, for faster transients than the transient. The only reason why we use that terminology is because there's so many different components in a power system with varying time constants that, right, you can have different types of transients. You can have transients that affect, that are transient from the point of view of the motor only. You can have transients that are so fast that they actually affect a transient response within the transmission lines or other components in the system. So there are different categories of transient. Okay, so How do the magnetic field lines connect the rotor and the stator? In the steady state, the armature reaction flux can penetrate the core. And the result there is a baseline value that we're going to call 1 per unit. Okay, all of these values are going to be relative to one another. So, we'll use 1 per unit as our starting point, the synchronous value. And then now what we're going to do is compare the transient and the subtransient values to that baseline. Okay, now, next, during subtransient periods, and subtransient is going to be the time immediately after the disturbance. When the dynamics are fastest moving. So we're going to go from steady state, disturbance occurs, we have subtransient, which is the very, very fast movement. Some of those dynamic behaviors will settle down, which will lead us to the transient period, which is a slower movement, and then we get back to our steady state. So during the subtransient period, the armature flux cannot enter the rotor. So during the subtransient period, we would expect a change in the flux linkage between the stator and the rotor. But previously, when we outlined the constant flux linkage theorem, what we said was that that cannot take place because of the two different factors, VF not changing and the time constant for that winding being very large. So during the subtransient period, that additional flux is not going to be able to penetrate the ferromagnetic core of the rotor. And what this means that much of the armature reaction flux will have to flow through the air gap. So what's the change between the steady state and the subtransient period? During the steady state, 99% or a very large percentage of the flux linkage between the rotor and the stator, that's flowing through the iron core of the rotor and is connected to the stator windings. During the subtransient periods, because of all the factors we've talked about just now, one of them being the constant flux linkage theorem, a lot of that flux, those additional flux lines, must flow through the air gap. Okay? If you remember right, we have the rotor, we have the stator, and in between we have the air gap. So we have a lot of that flux linkage is going to be flowing through that air gap, which is going to have a higher reluctance than the core. Right? It's easier for the magnetic field or the magnetic energy to flow through the iron than it is to flow through the air. And so higher reluctance means lower inductance. Or reactance. Right? Inductance describes the magnetic link between the stator and the rotor. During the subtransient period, some of that connection is going to be stifled, right? And so what we're going to see is a higher reluctance causing a lower inductance. And the inductance is proportional to the reactance. So what we expect is that the subtransient reactance value will be smaller than the steady state. And so we call this smaller value the subtransient reactance. And we'll use the variable xs double prime. $50 milliseconds, not 50 cycles. My apology. So disturbance occurs, constant flux linkage model applies or theorem applies. A lot of the armature reaction flux that normally would be flowing into the field winding can't. It's forced to stay in the air gap, which is going to drive the inductance value down. In this book, we're going to use an approximation of 1/7. And this approximation, it works well for about 50 milliseconds after the disturbance. Now, after the subtransient period comes the transient. So before I continue on, just to give a little bit of context of how this material is going to be used. So there's two different aspects of this, what we're talking about right now. Number one is the practical side of it. I could give you a problem which is asking you to solve for the terminal voltage, 100 milliseconds after a disturbance occurs. So being able to solve that problem involves a couple of steps. So number one, being able to recognize that 100 milliseconds using the thresholds and assumptions that we have in this book falls into the transient range, not into the subtransient range, okay? And then realizing that for this type of problem, you have three available values, right? You have XS, XS prime, XS double prime. And because we're in the transient period, you would be replacing the value of XS right here with the value of XS prime, and then calculating your solution. Other than that, there's really not too much to this. So that's the one side of it, is the practical side. The other side is the theoretical, and being able to explain why the different transient value, or the different reactance values exist. And, for these short answer questions, a lot of times we're looking for key words or key phrases that indicate you know what's going on. In my mind, there's two. Should I answer it? Let them talk to the whole class. There's two. Number one is constant flux theorem, right? Stating that whatever the flux linkage was between the stator and the rotor before the disturbance, that's going to stay the same. The second part of that is something about flux flowing through the air gap, right? Because of the constant flux linkage theorem and what that implies, during the subtransient and transient periods, some of the armature reaction flux is going to be forced to flow through the air gap, which is not as conductive, right? And that's going to drive the inductance and reactance values lower. So there's being able to use it and solve, and there's also being able or understanding why the values are a certain way and explaining that. And so again, another approximation that the book gives us is this approximation that the transient is double what the subtransient value is. Now we're not going to go too much into the transient, and because the transient is really just a mixture between the synchronous and the subtransient. Essentially, during the transient period, the constant flux linkage theorem begins to soften, right? Because now we're reaching a longer time period, which means that now some of the armature reaction flux will begin to penetrate the rotor, and that's the reason why the value begins to increase, right? Because the reluctance goes down. During the subtransient period, that's when we can say, okay, all of the armature flux armature flux reactance field lines are forced into the air gap during the transient period, where some are allowed back into the rotor. And then when we reach the synchronous period again, that's when we have a very high percentage, right, linkage between the rotor and the stator. Okay, so that's it for chapter 9. And I'm not going to include anything from chapter 10 on your quiz. I think it'll be good enough to maintain it as a chapter 9 quiz. So you can see here a lot of this quiz is going to be focused on the equivalent circuit, our analysis on power output, which was section 9.4. So for that analysis of power output, we were assuming that IF, the field excitation, was staying constant. And then section 9.5, which dealt with field excitation for reactive power control. And during that section, we were assuming that the the mechanical power in was staying the same. And then lastly, our discussion of synchronous, transient, and subtransient reactances, which is sort of its own animal. And on top of that, I would go through and review some of the material that was related to magnetics from the lecture before the March 28th lecture. All right. So, chapter 10. Is voltage regulation and stability in power systems. So how is this going to differ what we were talking about in chapter 9? Now we're going to slowly expand our point of view outward and begin to consider transmission lines, potentially situations where we have more than one generator bus, and really start to just look at it from more of a system-wide perspective. So, section 10.1, I encourage you to read if you have a chance. It talks about some pretty interesting issues, one of which is stress transmission lines. And how that contributes to greater stability issues. Maybe I'll say instability issues. So, one of the areas, and I think I talked about this a little bit in that first lecture, the PowerPoint that we did in the first class. One of the areas where we're really lacking, especially in the United States in our power system, is upgrades to the transmission network, right? There's been a lot of money put into building new generating units, but very little relatively put into building new lines. So it's sort of like this building where we have a foundation. They keep building new floors, more and more floors on top of this, on this building, but they never upgrade the foundation underneath it, which what really supports it. So transmission lines that are becoming increasingly stressed, what that means is our level, our region of stability is growing smaller. Okay, the more stressed those lines are, the greater effect they have on those flows have on stability. Now we're going to talk a little bit about the math behind that in this chapter, but the introduction just introduces the topic. And so in this chapter, we will focus on the electromechanical aspects of the power system. Writing on the iPad is weird. Does anybody write on the iPad a lot or do anything like that? It's fine for like the first 10, 15, 20 minutes, and then like an hour later, I think it's because the glass or it's so smooth or the pen's not really comfortable. Like it gets to the point where, like you see I make so many mistakes, like my hand literally cannot write anymore. I should just go back to pencil and paper or the board or something like that. Okay, so section 10.2. The radial system as an example. So here is one example system that we're going to use in this chapter to illustrate these voltage regulation and stability issues in a power system. Before, we just had the equivalent generator model connected to an infinite bus, and now what we're going to have is our ideal source. That's our bus connected to a transmission line. Connected to our load. We're going to go a little bit into transmission line modeling in this chapter. We're going to kind of cycle back to chapter 4 and touch upon that a little bit. Unfortunately, for a single semester class in power systems, it's just we don't have that much time to get into transmission line modeling. It's the one that's easiest to skip over. Let's put it that way. If there are transient effects, they're the fastest moving transients, which means they're more times than not going to be neglected. Okay, we focus on worrying about steady state, and then we often examine slower moving dynamics, and as we get faster and faster, it becomes harder and harder to analyze those. And also just in practice, from what I've seen, it's the component of the system that's most often just assumed to use a very simple model and say, okay, well, we'll throw this pi model up here, and that will be good enough. But we'll talk about it a little bit. So what do we have in this radial system? We have an ideal source. We have this bus, so this voltage will be called Vs. We have our pi transmission line, which is essentially the word pi because it looks like the Greek letter pi. We have two capacitors on either side, which represents the relative capacitance between the line and the ground. We have the resistance of the light itself. And we have the inductance. Over here, we have our receiving end voltage and our load, which will most times be described like that, PL plus JQL. The real and imaginary components of the power consumed. A lot of times, what we will do is we will take the capacitor at the receiving end and we'll aggregate that into the load, and we'll take the capacitance at the sending end and aggregate that into the source. So the transmission line will often be left with just the series elements, which will be the resistance and the reactance. And then obviously we have the current flowing. And that's it there. Okay, well, it's 9:15-ish, so I think we'll just go ahead and stop there. April 15th, there was a couple of people who came in late. April 15th will be the due date for your project. All that stuff now